This is Lecture 1 in Module 6 in the book Problem-Solving Guide for Electromagnetism and Optics. This is all about resistors in circuits. Module 4, we talked about capacitors. Module 5, it was electric current. Here, resistors in circuits. Resistors, like capacitors, are common components of electric circuits. Here's a circuit board. It's got some resistors, got some capacitors. Here's a resistor right here. Here's another one. Blue things are capacitors. That's a capacitor right there. Another one right here. Another one right here. That's a capacitor. The symbol for a resistor in a circuit is squiggly line, or sometimes we are lazy and just draw a rectangle. The variable is capital letter R. So let's look at a circuit with only a battery and a resistor in it to see what it looks like. Something like that. There's the battery, there's the resistance, there's the V, there's the R. So there's a constant flow of current around the circuit, unlike with a capacitor. Capacitors are dead ends. There's no way the charge can get from one side to the other unless it breaks down. So we have a current going through this circuit. V is equal to IR. The stronger the voltage, higher the voltage, the more current, the lower the resistance, the more current you get. You can write it as I equals V over R. R's in the denominator. The lower R is, the higher the current. The current is directly proportional to the voltage of the battery, inversely proportional to the resistance of the resistor. So what's the voltage across this resistor? It's the same as the voltage of the battery. There's only one element there. So the equation V is equal to IR is used for every individual resistor, and it can be used for the entire circuit as well if there's a whole bunch of resistors up there, the equivalent resistance of the circuit. So let's think about the units. R is a volt per amp. A volt per amp has been given a name. It's called the ohm. It's a volt per amp, and the symbol is the capital letter omega. So a resistance of 15,000 ohms, this can be written as 15,000 with a capital letter omega. The resistance of the wires themselves, there is some resistance, but it's much, much smaller than the resistance of a resistor in the circuit. The resistors on the circuit board were 15,000 ohms. If you have a 10-foot length of 12-gauge copper wire, it has a resistance of 0.016. So we don't really include the resistance of the wires in the circuit because it's so small. Virtually all of the resistance is in the resistor. Electrical resistivity is an intrinsic property of a material. Here's some resistivities. Copper is 1.7 times 10 to the minus 8th ohm meters. Silver is a little bit better. Aluminum, iron, gold. Now those are conductors. Very low resistivities, 10 to the minus 8th. Non-conductors like diamond, 1 trillion ohm meters. Hard rubber is 10 trillion. Glass, 100 trillion. Dry wood, 1,000 trillion. Air, even higher. Teflon, much, much higher. The resistance is freaking huge. The difference in the resistance of a conductor and a non-conductor is many, many, many orders of magnitude. If we have a wire, we want to know what the resistance is, we can use the resistivity and its length and its area. The longer it is, the more resistance it has. The bigger the cross-sectional area, the lower the resistance. It should make sense. If you have a big pipe, it's not going to have resistance to flow. The longer the pipe is, the more the resistance. Now, of course, the cross-sectional area doesn't have to be a circle. There's rectangular bus bars that carry current. You have to avoid plugging in the resistivity, the Greek letter rho, for the resistance in V is equal to IR. It's important to understand the difference between the two. V is equal to IR. That's the resistance, not the resistivity. You can look up the resistivity of an element or alloy in a table, but the resistance depends on its dimensions. So now let's consider a circuit with two resistors. There's a circuit with two resistors, R1 and R2. These are in series, one after another. There's no option for the current. There's no branching. So let's look at this. What is the current in this circuit? What is the equivalent resistance? These are the questions we're going to ask. What's the voltage drop across each resistor? How is the voltage drop across each resistor related to the voltage of the battery? So let's see. The voltage drop across resistor 1 is the current through R1 multiplied by the resistance R1. V1 is I1 R1. Same thing for resistor 2. That's true all the time. What we want to know is what's the equivalent resistance of this circuit. So the electrons are going around the circuit. It's a single loop, like a merry-go-round. It's all going around. The number of electrons going through this resistor per second has to be the number of electrons going through this resistor per second if it's one loop. Got to be. Makes sense. There's no branching. Where else can they go? So we can drop the subscripts on the current. The current going through R1 has to be the same as the current going through R2. So I1 equals I2 equals I. There's only one I in this circuit. The sum of the voltage drops across the resistors is equal to the voltage drop across the battery. We're going around a circuit. So V1 plus V2 is the voltage of the battery. And we can substitute in for V1, it's I1 R1, or just I R1. V2 is I R2. We can factor out the current, and this is because the current's the same, and this is the equation for the equivalent resistance. V is I R equivalent, so R equivalent is R1 plus R2 for two resistors in series. If that's a 30 ohm resistor and that's a 60 ohm resistor, the total resistance is 90 ohms. You just add them up if they're one after another. If you want to increase the resistance of a circuit, add a resistor in series. The equivalent resistance of two resistors in series is just the sum of their individual resistances, and you should understand that. If you want to lower the current in the circuit, you have to increase the resistance, and you just force the current to go through more resistors. Simple as that. If you're talking about the flow of water, the length of the hose is certainly a resistor. And if you want to add more resistance, you do that. You crimp it. It's like adding a resistor in series. The flow is going to drop. All the water has to go through that crimp. There's no branching. Now let's consider a resistor in parallel with the first. So now we're going to not consider series. One like this in parallel. There's an option. The current can go through this one or that one. What's going to happen to the current through the battery? Stop and think. In this configuration, the voltage across each resistor is the voltage across the battery. This resistor is right across the battery. From one side of the battery to the other, nothing in between. This resistor is also across the battery. Each have the same voltage, and that's the voltage of the battery. You can go V1 equals I1 R1, V2 equals I2 R2, same as before, but in this case, the current is different, and it is the voltage that's the same. That's the voltage of the battery. They're both across the battery. So we drop the subscripts on the voltages. We don't call them V1 and V2, they're just V's. V1 equals I1 R1, V equals I2 R2. The equivalent resistance, as always, is V is the current through the battery times the equivalent resistance of the circuit. Now what about this current? The current comes out of the battery and it splits. Some of it goes around this loop and some of it goes around that loop. Some of it goes through R2, some of it goes through R1. All go through the battery. There's no option there. The battery pumps them out. They can go around that loop or that loop. The current through the battery is the sum of the current through resistor 1 and the current through resistor 2. I through the battery is I1 plus the current going this way plus the current going that way. And this is backwards. I have to pause here and tell you about the fact that humans guessed wrong. Humans guessed that it was the positive charge that was moving, but in fact it's the negative charge that's moving. So conventionally, on circuit diagrams everywhere, still, this capital I is the direction of the positive current. But there is no positive current. The nuclei stay in the same place in a metal. It is the electrons that move. So the electrons are actually flowing this way, but we still say the current is going that way. And for most applications, it's fine. Positive current flowing counterclockwise is the same as a negative current flowing counterclockwise, and vice versa. Back to the problem. We need expression for these currents, and we can use V is equal to IR. I1 is V over R1. I2 is V over R2. That's just V is equal to IR. We can add up the currents to get the total current through the battery. And we can use the equivalent resistance equation. I is the voltage of the battery divided by the equivalent resistance. Substitute that in right here and cancel out the V's. And we get this expression. So when you add resistors, another resistor in parallel, this is the equivalent equation for the equivalent resistance, and the resistance goes down. The resistance of the circuit is lower than R1 and it's lower than R2. And the reason why the resistance goes down is you're giving another branch for the current to go. The current's going to go up. If the current goes up, the equivalent resistance has to go down. And of course, adding a second resistor here has no effect on the current through R1 because R1 has a voltage V across it, the voltage of the battery, and V is equal to IR. That's independent of what the value of resistor 2 is. So now let's start over. We're going to go through everything again slowly, and this time with numbers. We're going to use a 12-volt battery and a single 60 ohm resistor, like that. 60 ohms, 12-volt battery. We can get the current. V is equal to IR, and that's 200 milliamps, a fifth of an amp. 12 divided by 60 is a fifth. 200 milliamps going around that circuit. Now we're going to add another resistor right here, parallel, 30 ohm resistor. There it is. The current through the 60 ohm resistor does not change. There's still 12 volts across that. How much current is the 30 ohm going to draw? Well, it's got half the resistance. It's going to get twice the current. V is equal to IR. It's 400 milliamps. So if there's 400 milliamps going through this one, 200 milliamps going through that one, how much is going through the battery? 600. And it splits like that. 600 comes into this junction, 400 goes that way, because it's easier to go that way. The resistance is half as much, it's going to draw twice the current. 200 amps goes that way. Current through the battery, 600 amps. Conservation of electrons. Current going into a junction has to be the current going out of the junction. I don't know what that means. Conservation of voltage. Voltage shouldn't be conserved. Let's think about this. And I got an analogy for you. Water, a water analogy. This is my version of a water tower. Good guess. That's a water tower. And these are houses. And the water tower supplies water to the houses, and the reason why it's up in the air is so there's high pressure. So when you turn your faucet on, the water comes flying out. The height of the water produces the pressure. All the houses have the same pressure. It's about 50 psi. And you wouldn't add these pressures up to get 200 psi. Doesn't make any sense. There's no conservation of water pressure. Right? That's not the total pressure. If I put another house there and hook it up to the water supply, it's going to read 50. But that's not 250 psi. Everybody's got 50. Now, if we talk about flow rate, this house has 2 liters per second. This house has 3 liters per second. These two houses don't have anything. The flow rate out of the water tower, net, is 5 liters per second. Water is conserved. You can't create water. Just like electrons. The voltage in a circuit is analogous to the pressure, right? If I add another resistance in series, I got the same voltage. In parallel. It's the voltage of the battery. I can add another resistance in parallel. I'm not adding more voltage. It's all the same voltage. If I add another house, I'm not adding more pressure. It's the same pressure. But the electrons are conserved. The electrons are the things that are moving through the circuit. The voltage doesn't move. Voltage is the energy it gets when it goes from one to the other. Why should that be conserved? Doesn't make any sense. Okay, let's go back to this circuit. So the battery behaves as if there's only one resistor up there. The battery tries to push charge, and it pushes this current from one side to the other as if there's only one resistor up there, and that is the equivalent resistance of the whole circuit. Let's calculate what the equivalent resistance is. In parallel, there's the equation. We have a 30 and a 60, and we make the 1/30th 2/60th, so I get a common denominator. We get 3 over 60 ohms is 1 over our equivalent, so the equivalent resistance is 20 ohms. The 12-volt battery thinks there's 20 ohms up there, and if you have a 20 ohm resistor, you hook it across a 12-volt battery, it's going to get 600 milliamps of current, and that's exactly what the battery does. The battery doesn't know it's splitting up here. The battery is just feeling the resistance of the circuit and pushing electrons from one side to the other. So it all makes sense. So now with an understanding of how resistors combine in series, in parallel, and the concept of electric current splitting at branches, you can tackle some nice complicated circuits. So this conservation of electrons law is stated: number of electrons going in equals the number of electrons going out. It's not rocket science. So there's some great examples in your textbook of complicated circuits. Here's example 2. There's the figure. Battery is hooked up across AB. All right, Victron pulls electrons out at B and forces them in at A, and they go around the circuit and come out at B, and the battery puts them back in at A. Each resistor is 300 ohms. If I hook up a battery here, how much current does it get? And of course, there's a whole bunch of different ways to ask this question. You can put A and B here across this resistor. You can put it all the way across the bottom here, and you can put it all the way across the diagonal. There's a whole bunch of ways to ask this question. What a wonderful opportunity to develop your problem-solving skills. I'm jealous.